Hello, my name is Richard DeMello, and I'm a software engineer within the KV engineering team. With my colleague Asad, who's a software engineer in test, we'll be taking a dive into Jepsen testing at Couchbase. During this presentation, we'll cover what the Jepsen project is, give a crash course on consistency guarantees and why they're important, summarize the durability options and auto-failover functionalities of Couchbase Server, and then look at how we're using Jepsen at Couchbase. So, what is Jepsen? The Jepsen project was founded by Carl Kingsbury with the aim of improving the safety of distributed systems by holding them to account. They've tested the consistency claims of the largest distributed systems, with a few of them named here. The Jepsen project can be thought as two parts, one being the talks and educational content provided by Jepsen to help better inform people about distributed systems and consistency, and the second being the testing and consultancy that Jepsen performs and the open source software that they've created to assist this. Jepsen has currently released 4 main open source projects to help better understand distributed systems and test them. The first of these being the Jepsen test framework, which allows users to test their own distributed systems by introducing failures into the system. L, developed in collaboration with Professor Alvaro, helps to perform testing for transactional consistency and now comes packaged with the Jepsen framework. Knossos, a library that takes history of read and write operations and tries to verify whether or not they meet a consistency model, for example, linearizability, and comes packaged with the Jepsen framework too. Finally, there's Maelstrom, a workbench for helping to learn about distributed systems. I'm now going to hand over to Asad, who's going to explain why we need consistency models and how Jepsen checks for them.
Thanks, Richard. Hi, I'm Asad, and I'm a software engineer in test, and I'll be exploring consistency in the context of reads and writes to a single Couchbase document. So, why are consistency guarantees important? Strong consistency guarantees make reads and writes predictable. In this diagram, time moves from left to right. Given a single client Bob performing operations on a single document or variable which is initially 0, suppose we have a read of 0 followed by a write of 5. What should the final read operation return? We expect Bob to read 5. In single-threaded applications, we have an intuitive notion of operations happening in the order they were issued in. Predictable reads and writes make systems easier to reason about, and therefore easier to develop applications against. Developers are used to working with variables in single-threaded applications, and assume reads and writes to databases are similar. However, strong consistency guarantees are required to make such assumptions. In particular, under high concurrency workloads, illustrated on the left, and when faults are introduced into the distributed system, such as disk failures or network interruptions, illustrated on the right, we require a consistency guarantee, a contract between the developer and the database to ensure reads and writes are predictable. That's where Jepsen comes in. We make use of Jepsen testing to ensure that we are consistent, while faults are introduced into the system. This diagram of consistency hierarchies shows the guarantees below in orange and blue are weaker, but available. The guarantees at the top in pink are stronger, but instead are unavailable. They compromise on availability. The default configuration of Couchbase is eventually consistent and offers high availability and low latencies. Strong consistency guarantees are easier to work with, but enforcing them involves a communication overhead and compromises on availability. So, how does a Jepsen test work? Jepsen testing involves writing an adapter layer which allows Couchbase to be driven by Jepsen. The first step in a test involves Jepsen spawning workers which will spin up a Couchbase cluster. In this example, Jepsen has spun up a Couchbase cluster consisting of 3 healthy nodes. Jepsen produces client operations. We model Couchbase documents as compare and swap registers, or more simply as variables. Client operations consist of reads and writes. Operations have a return value. This is indicated by the arrow. Read operations return document values, whereas write operations update document values. A special operation called compare and swap accepts 2 arguments. An update is only performed if the first argument matches the document value. If the initial document value is 4, the cast 4, 5 shown above will successfully update the value to 5. However, the cast 2, 5 shown below will error, as the first argument 2 does not match the document value 4. Jepsen generates a highly concurrent workload and fires numerous randomized key-value client operations at Couchbase across a set of logically single-threaded processes involving multiple documents and nodes. Faults such as node failures are simultaneously introduced into the system via a special Nemesis client to disrupt normal operation of the distributed system. In particular, Jepsen introduces faults such as network partitions, a type of internode communication fault known to manifest consistency errors in distributed systems. In this example, the orange nodes and the green nodes have been partitioned by the Nemesis and can no longer communicate. Jepsen will record the concurrent operation history. The history, illustrated on the left, is a record of which operations happened, the client that produced each operation, when they began and completed in real time, and finally, what each operation returned. The history is then analyzed through a checker for correctness, given a consistency guarantee and a data type, for example, a compare and swap register. A checker determines if the history is correct and conforms to the consistency guarantee. Hence, one definition of a consistency guarantee is a set of histories that are deemed legal and correct by a checker for that guarantee. A consistent system will always yield legal histories under the rules of the contract. In order to define correctness, we'll look at 2 strong consistency guarantees: linearizability, which the checker Knossos checks for, and sequential consistency, a model which SeqChecker, a per-register sequential consistency checker, uses. Previously, we were presented with a single client history, and we had an intuitive understanding of what it meant for the history to be correct. However, what does it mean for a concurrent operation history to be correct? To address this, we can ask a similar question to before. What can we expect the read operation issued by Charlie to return? We can consider time. Given a history, we know the start and end time for each operation. This is depicted by using vertical bars at the start and end of each operation. Furthermore, some operations precede others in time. There's a returns before dependency between operations that starts after another operation ends. Operations that overlap are not ordered by this dependency and are concurrent in this context. In this example, Bob's write 5 and Charlie's read ? Are concurrent because neither operation returns before the start of the other operation's end. So what can we expect the read operation issued by Charlie to read? Well, operations are not instantaneous, but instead take time. We can visualize this as a message being sent at the start of each operation to some source of truth, for example a database, to be processed, at which point the document state changes, for example from 0 to 5. A response is sent back as confirmation. In this case, Charlie's read returns a 0 because it arrives before Bob's write and is processed first. Messages can arrive faster or slower, and consequently, the delay between sending and receiving a message results in some ambiguity. If the read operation arrives after the write and is processed after the write, the read operation returns a 5 instead. However, operations cannot take effect before their start, as messages cannot be sent backwards in time, and they cannot take effect after their end. Operations must take place atomically at some point between their start and end. We can depict this visually using linearization points, a vertical bar present between the start and end of each operation, as an explanation for this particular history to indicate when the operation appears to take effect. We can draw arrows between linearization points, and consequently, we can order operations by when they appear to take effect. This gives us a sequential, single-threaded operation history. This is called the single order property, which is illustrated below. Essentially, a sequence of operations as if they were issued by only a single client. Furthermore, the arrows must point forwards in time. The sequential order is consistent with the returns before dependency. This is known as the real-time constraint, with a little bit of bookkeeping to account for ambiguous operations. If operation A happens before B, illustrated by B having a lighter purple shade than B, then A precedes B in the sequential order. In this example, lighter shades must come before darker shades in the sequential order. However, operations with the same shade of purple are concurrent and can be interleaved arbitrarily with respect to each other. The sequential order must also obey the single-threaded rules of the data type. This is known as the RVal constraint. In this example, David's cast 2,4 succeeds after reading 5 and updates the document value from 4 to 5, which would be invalid in a single-threaded history. Replacing the first argument of the invalid cast operation with a 5 allows the single-threaded loss to be preserved. Combining single order, real-time, and RVal gives us linearizability, a strong consistency guarantee. There exists some total order of operations that is consistent with the real-time order of operations and obeys the single-threaded rules of the data type. Clients agree on the order of operations and when they happen. However, the real-time constraint limits the possible legal interleavings and therefore comes with a scalability and performance costs. Therefore, we must relax our consistency model without compromising on intuitive correctness. To address this, we can turn to client order, a dependency between operations imposed by the order that were issued by their respective client. Let's suppose Bob is throwing a party and sends out an invitation. Unfortunately, it starts raining, so Bob decides to cancel the party. In this example, Bob's client order is write invite, write cancel. Client operation pairs are now concurrent if they are produced by different clients. For example, Bob's purple operations are concurrent to Charlie's yellow operations. This leads to the PRAM constraint, a property that is satisfied if any pair of writes issued by a client are visible to all in client order. Without PRAM, it would be possible for another client to observe the cancellation before the party invitation. Similar to real-time, in which the sequential order is consistent with returns before, the PRAM constraint is satisfied if the sequential order is instead consistent with the client order. If operation B follows A in client order, illustrated by A having a darker shade of the same color than B, then operation B must follow A in the sequential order. In this example, it means the same colored operations must get darker further into the sequential order. Relaxing real-time to PRAM gives us sequential consistency. There exists some total order of operations, which is consistent with client order and obeys the single-threaded rules of the data type. Clients agree on the order of operations, but not necessarily when the operations happened. A strong guarantee in which any history is equivalent to some sequential interleaving that obeys single-threaded laws and is consistent with the client order. What's the catch? Similar to the linearization points, we can draw a vertical line to indicate when the operation took effect. However, operations can now take effect outside of the start and end times. In this example, Bob's write 5 returns before Charlie's read 4. However, in the sequential order, Bob's write 5 is after Charlie's read 4. This results in an arrow pointing backwards in time, a possibility that was previously not allowed under linearizability. However, this is allowed under sequential consistency, in which operations can take effect outside of the start and end times, as long as client order is preserved. In this case, we simply draw the justification lines to indicate Charlie's read operation took effect at an earlier moment in time. This is illustrated by the dotted boxes to the left indicating when Charlie's read operations took effect. This is an example of performing a stale read from a cache. Many systems which behave like caches are sequentially consistent, particularly systems in which messages trickle through several layers of caching systems. Although, clients can be arbitrarily ahead or behind in time. Sequential consistency is in fact quite a strong guarantee. This is a consequence of the session guarantees offered by the PRAM constraint. A subsequent purple read returns a cancel. This is known as read-your-write consistency. Every client agrees that invite is followed by cancel. This is known as monotonic write. And finally, a subsequent yellow read operation can no longer observe invites once a cancel has been seen. This is known as monotonic reads. Given that we have a good understanding of consistency guarantees and what Jepsen testing involves, I'm going to hand it back over to Richard for an overview of Couchbase's fault-tolerant and durability options, and to explore how we use Jepsen at Couchbase to test its durability levels.
Over the next few slides, we'll take a quick look at the spectrum of durability levels on offer when using Couchbase Server. The first and lowest of these, known as none, is how all KV operations were performed before 650. It provides eventual consistency and is highly performant due to its scaling very well and providing very low latencies. Persist to majority, the highest level of durability. This adds the requirement that we must persist the document to a majority of replica nodes, as well as the active. This does add more latency as we're now waiting for disk on multiple nodes, but helps us to handle 2 consecutive failures. For instance, if an active node lost power and then the replica crashed and restarted within the auto-failover window, we would still have a copy of the document on disk of the replica, which can then be promoted to active. Majority. This ensures that the document is replicated to a majority of replica nodes in memory, allowing the client to know that a document has been replicated in the case the active fails and has to be failed over. This can be thought as in-memory durability and is the only durability level on offer to ephemeral buckets. Finally, majority and persist to active. This builds on majority, adding the requirement that we must also persist the document to disk on the active node. This helps to prevent against data loss in the situation that the active crashes before persisting a document and then comes back online with the auto-failover timeout. As the last few slides have shown, auto-failover plays an important role in durability. I'm now going to briefly cover the 3 different events that may trigger it. The first of these being a node becomes unresponsive for some reason. For instance, the node gets partitioned off or loses power. Failing over the node will allow us to make forward progress for the rest of the cluster, as the replica vbuckets can now be promoted to active. The second event is when the disk read and write failures hit a significant rate of failure. In this case, we want to fail over the node, as any non-persistent durability ops will still be written to memory, but may never be written to disk. Finally, we can perform auto-failover on a group of predefined nodes that share common infrastructure. For instance, a rack, cloud zone, or VM host. For instance, we may need to fail over a subset of a cluster if a VM host was to crash, taking out multiple nodes in the cluster. In this case, the cluster would also need to be large enough to ensure that it could handle the extra workload of the failed over nodes. In this section, we're going to take a look at the types of testing that we perform using the Jepsen framework. Currently at Couchbase, we're using the Jepsen framework to test consistency in 2 main areas. The first of these being our data service when performing key value operations, which we test for linearizability and sequential consistency. Though in most cases, we check for linearizability given it's a greater level of consistency. We run 46 tests on the nightly builds and 8 on every single commit added to the data service, which has led us to find 52 bugs, though the majority of these were found during 650 development. The other area is Chronicle, our consensus protocol on the RAF based on the RAFT algorithm. This is used by the cluster manager for metadata management, for instance, cluster configs and settings. We run 8 tests each night checking for linearizability. In the next few slides, I'm going to look over the 2 main types of workloads that we run against the data service. Firstly, the register workload. This is designed to check for linearizability. However, at Couchbase, we've also added our own version that will allow us to check for sequential consistency too. The workload works by creating a set of documents which are treated as registers, like in a processor. Each register has read and write operations performed against it by a number of Couchbase clients. Jepsen records the result of each one of these operations. In the diagram, you can see the swim lanes that represent the client's history, with successful operations shown in blue, failures shown in pink, and ambiguous results shown in orange. If a client sees an ambiguous result, then the client is closed and a new one is spun up. During this, we will also introduce a failure, also known as a Nemesis, to see if we can cause a consistency failure. So I've mentioned a little bit about Nemesis, but I wanted to share with you the sort of Nemesis that we perform on the cluster while testing. Currently, we have 4 broad categories. The first of these being process state, where we can play with the execution of a given process of Couchbase Server by performing a hard reboot, killing a process, or pausing it for a given period of time. The next area is disk, where we can affect the performance of the underlying data store by performing a device loopback, for instance, slowing down ops or failing reads and writes altogether. Network partitioning. We can isolate a node so it can't communicate with the rest of the cluster, but can communicate with the client, or that 2 nodes in the cluster can't see each other but communicate with the rest of the cluster. And finally, cluster state changes allows us to check Couchbase Server functionality of failure and rebalance do not affect consistency while being performed. Jumping back to the register workload, the recorded history is then passed to Knossos, which analyzes the history to check to see if it was linearizable or sequentially consistent. If there was I'll just start the slide again. Jumping back to the register workload, the recorded history is then passed to Knossos, which analyzes the history and checks to see if it was linearizable or sequentially consistent. If there was a linearizability failure, then Jepsen will create a diagram explaining the failure, as can be seen in the example that we've created. The diagram shows that there are no linearization points that can justify linearizability due to the fact that client 120 read a null value after client 32 performed a write of value 2. The second workload I want to talk about is a set workload. This is designed to ensure that no writes are lost when performing multiple concurrent writes, while a failure is introduced into the distributed system. We're able to get much higher throughput during this test than the register workload due to the test only performing isolated writes. This also makes the analysis far less complex. The workload starts off by creating a pool of Couchbase clients. Each of these clients creates documents from a set of predefined keys. During this, we may introduce a Nemesis to the distributed system. Once the set of documents has been written, we perform a read of all the documents from the database, checking the state of the database against what was reported to Jepsen about the result of each operation, to ensure that if there have been no lost writes or writes that were said to have failed have actually been written incorrectly. Looking forward to the future of Jepsen testing at Couchbase, we hope to expand our Nemesis and workloads, for instance, performing multiple Nemesis within a single workload, adding clock skew, and creating a new network partitions. We'd also like to add more workloads like the Jepsen bank test and add more types of clients, for instance, creating a nickel client and expanding transaction testing with L. So in conclusion, data consistency is something that we care passionately about at Couchbase. We hope you found this talk has provided a better insight into Jepsen, our testing at Couchbase using Jepsen, and durability levels to best balance your performance and consistency needs.